Hello everyone, today I'm going to be talking about my CS444 final project. So for my final project, I was really interested in attacks on machine learning models and possible defenses. So let's talk about these attacks and why they're such a problem. The main attack that I'm going to be interested in for the rest of my presentation is this addition of noise. So specifically, we have noise with maximum intensity or maximum value of epsilon. We add it to an original image, and we force it to misclassify. And there are many attacks which an intelligent adversary can use to force a model to misclassify. And in this specific case, it might not be as big of a deal if you're just using a classifier. However, in some safety critical applications, this could have huge implications. For example, if you're an intelligent adversary, you could use this to crash a self-driving car if it misclassifies, for example, a car as a pedestrian or something like that. So we really want to make sure that our models are robust to these types of attacks. And the fundamental property that we're interested in is, we can colloquially define it as, if an image looks the same to a human, it should classify the same for a machine learning model. And the way we define this property is we again use the intensity of noise. We say, with any possible combination of noise with intensity at most epsilon, the image will still be classified correctly. So let's take a look at some attacks and also some defenses that we can use to find these adversarial examples. Going forward, I'm going to be calling images like this one, which are misclassified adversarial examples. So there are two different types of attacks that I used. The first one is called FGSM, and the second one is called PGD, and they both work in a fairly similar way. We assume the network is fixed, and we want to modify our X. So what we'll do is we'll compute the forward pass on X, compute the loss, and then take a step on gradient ascent on X, or in the case of PGD, we'll take multiple steps to increase the loss as much as possible. And we always make sure to clip the input back into the epsilon neighborhood of the original image. So I ran this attack on several different models. I ran it on a network that had a lot of linear layers that looked something like this, 2 convolution layers, lots of linear layers. I ran it on a fully convolutional network, which looked something like this. As you can see, it has, I think, 5 convolutional layers and just 1 linear layer. And I also ran it on a pre-trained ResNet to see what the results, give me 1 second. Yes, the ResNet is right here. I also ran it on a pre-trained ResNet to see what the results would be like. And in all 3 cases, unsurprisingly, I was able to achieve very high accuracy on the validation set. And I was able to achieve, also unsurprisingly, over 90% accuracy on the training set using all of these models. So next, let's talk about how I attack these models. So what I did is I took the training set, I ran FGSM or PGD on each image within that set. And the set that was generated by doing so is called the adversarial set. And I'll be defining adversarial robustness as the accuracy that we get over this adversarial set. So if I scroll down, as we can see, even though these images are very close to the training images, the data that the model actually trained on, the robustness is extremely low. For example, for the simple network, it's 29%. Even ResNet is vulnerable to these types of attacks. And the fully convolutional network, which I actually expected to be better since it had less linear layers and I thought it would be less prone to overfitting, did even worse than these two. And as we can see, when we go from FGSM to PGD, the accuracy actually decreases slightly on ResNet, and interestingly, it increases on ConvNet, which I wasn't able to explain. So the first thing that I tried to fix this is I said, all right, let's train with data augmentation. Data augmentation is designed to make machine learning models less susceptible to noise. And so I added in random horizontal flip, random crop, and color jitter. I wasn't able to get auto augmentation to work, unfortunately. And I forgot to mention this earlier, but I'm also running on the CFAR dataset. I was unable to get ImageNet because it's 155 gigabytes and I simply don't have enough compute to be able to do anything with ImageNet. So the results with data augmentation were slightly better than without, especially for this case in ConvNet. It almost doubled the robustness. The reason I didn't run this on ResNet is ResNet was already taking a very long time to train. So I tested this, and I didn't report the results, but I remember when I tested it, I got similar numbers for no augmentation and data augmentation, so I opted not to run the analysis. But as we can see, even with the data augmentation, we're still getting very low robustness. And I've also included some images here. The image on the left is the original image in the dataset, and the image on the right is the version that was generated by FGSM. And as we can see, they look completely identical. So again, we want to prevent machine learning models from classifying these differently. So as we've already established, adversarial robustness cannot be achieved through data augmentation. So the next idea I had is we still don't need to modify the original models themselves, but instead we can define an adversarial loss function. Instead of using a standard loss like cross-entropy loss, first we evaluate our attack function, either FGSM or PGD, on the original images. This will generate an adversarial set, and then we compute the loss with respect to the adversarial set rather than the training set images. And what this will do is it'll make sure that even the worst case example, or at least the worst case that we're able to generate with gradient ascent, is still very reasonable and classifies correctly. So I reran the models once again with this. I unfortunately was not able to get the fully convolutional network to train, so I won't be using results for it going forward. But as we can see, there is a little bit of a drop in accuracy, almost 10% in both of these networks, which is unfortunate. However, we can see that the adversarial robustness went up quite significantly. In fact, in both of these cases, the adversarial robustness is almost 50%, both for FGSM and PGD. Now, you might be saying, we've proven that we can render a network robust to these types of attacks for images on the training set, but how do we know it'll generalize to images on the test set, or even just generalize to other types of attacks as well? And we can't prove this empirically, but one thing we can say is, in practice, the PGD adversarial training seems to generalize well to the testing set and also generalizes well to other types of attacks. In fact, this paper right here makes the argument that PGD is actually the most robust way to train a model because in some sense it's the best attack that we can formulate. So this was my presentation, and thanks for listening.